So we're going to continue chapter 5, and I'm just going to take a brief parenthesis from discussing cache architecture to introduce this concept of average memory access time, or AMAT, um, because it's going to be important as we discuss the next topics of the cache performance and the cache architecture. So the average memory access time is defined as the hit time. So that's the time that it takes an item to be delivered to the CPU by the level 1 cache if there is a hit, plus the miss rate times the miss penalty. So that is, so we discussed the miss rate. That's how many misses we have as a percentage. But then that is multiplied by the miss penalty, which is the time that it takes to recover from that miss. And that entails going to the lower level of memory, getting the block, putting it in cache level 1, and then delivering that item to the processor. And in the meantime, the processor is being stalling. So that's why I'm doing nothing. So that's what we call that a penalty. So as an example, if you have a 1 gigahertz CPU, so that would be 1 nanosecond clock time, and that would be the hit time. So we're assuming that the level 1 cache is keeping up with the CPU. But then if you have a miss, you have to go and get the block from either level 2 or main memory. And let's say that that takes 20 cycles now. And you have, just for the instruction side, because we know that we have split instruction and data caches, just for the instruction side, we have a miss rate of 5%. So in that case, the average memory access time would be this hit time times the miss rate here. So that would be 0.05 times 20. And we know that the clock cycle is 1 nanosecond. So you can calculate the average memory access time from there. So here you go. The hit time is 1 nanosecond because it's 1 clock cycle. Miss rate 0.05. Miss penalty 20 cycles, so that's 20 nanoseconds. So the average memory access time becomes 2 nanoseconds. So now you have 2 cycles per instruction. So effectively, between the miss rate and the miss penalty, you have halved the performance of your CPU. Essentially, when it comes to memory accesses, instead of being a 1 nanosecond CPU, now it's a 2 nanosecond CPU. So a 500 megahertz CPU instead of a 1 gigahertz. So it has big implications, and you can see that what we can do to minimize this, there are 2 variables that we can manipulate. We can either make the miss penalty lower or make the miss rate lower, or a combination of those. But those are the 2 variables that we can manipulate. All right, so that was a parenthesis about that concept, because when we talk about cache performance and access times, we're going to be, keep in mind that we're going to be referring to average memory access time. Now, up to now, or last time, what we saw is a cache which is called direct mapped, and each block in the lower level of memory mapped to only a single block in the cache. And we know that the cache is smaller, so we had multiple blocks at the lower level mapped to a single block at the higher level, the cache. But each block at the lower level mapped to only one single block in the cache level. What we're going to discuss, starting with this slide, is associativity. And what that means is that instead of one block mapping to only a block in the cache, one block in the lower level mapping to a single block in the cache, we're going to have a block be able to map to multiple blocks in the cache. So that gives us flexibility, because when we have to replace a block, we are not forced to replace that one block to which the block in the lower level maps in the upper level in the cache. We have some choices. At one end of the spectrum, we have what is called fully associative caches, which means that a block in the lower level can map to any block in the cache. So that's a lot of flexibility. And of course, that is more complex. What is going to require, and you're going to see in the diagram when we see that, is that now we're going to have to do searches in parallel for the tag, because now the block can be in any block. If we're talking about fully associative, it can be in any block. So we're going to have to do a lot of parallel searching, and those comparators, and they're going to add up. So it's going to be more expensive, okay, because we have to do those multiple searches. Now, n-way associative, n-way set associative refers to where we restrict the number of blocks in the cache to which a block in the lower level can map to a fixed number. And normally it is a power of 2. So we can have 2-way set associative, 4-way, 8-way, 16-way, and so forth, 32. Now, before we keep talking about this, it is important to talk about why would we want to do that. I mean, after all, if we are exploring associativity, isn't the block that we're going to replace sort of a stale anyway? And the answer is no. It's not, because associativity doesn't work backward from the cache to the lower level. So it could be that you are referencing an item that is in, let's say, block X, and you reference it, and that block X maps to a block in the cache. And now, next, you reference an item that is in block Y, which also maps to the same block in the cache. And so you go and replace what you just put there, because you had put X, and now you put there Y. But now you reference something in X again, and now you have to go back and replace Y. So there are software cases and software constructs that exhibit this behavior, and you can be in a situation where you're constantly missing and you're constantly replacing the block. And if you had the flexibility, once you have a miss for X, put X in a block, and now you have a miss on Y, and you have the flexibility to put Y in a different block in the cache without replacing X, you have both blocks now in the cache. So it increases your hits, therefore decreasing your misses, and improves your performance. So that's what we're going to be talking about for the next few slides. Again, fully associative is just that the block in the lower level maps to any block in the cache, and then n-way refers to just a set number, so it's smaller instead of all. And that becomes a design parameter as you are selecting the policies and the sizes of the block and the number of and the number of entries in the cache. So now another parameter is how many sets in terms of associativity. So here we have, if we have 8 entries in the cache, or 8 blocks in the cache, and we organize them this way, that would be direct mapped for a given size of the cache for the data that we're going to have in the cache. So in this case, we have 8, let's say 8 words. Now for the same size of cache, meaning 8 blocks, I can organize it this way. So I have 4 here and 4 here, and then the tag is next to the block, so I still have that. But now this become a two-way set associative, same size of a storage. It's not more expensive when it comes to storage, it's just more expensive when it comes to the searches that you have to do. Because here, I just have to search one tag, but here I'm going to have to search 2 tags in parallel, because a block could be in this set or in this set. Also, the number of bits that map to the line gets reduced. So here I have 8 possible entries in the cache, so I'm going to need the 3 bits to index the cache line. Here I only have 4 lines, so I only need 2 bits. But the line is wider. The line has 2 sets. This one, each line has 1 set, which is direct mapped. So that's the conceptual organization of associativity. This would be 4-way set associative for the same size, 8 blocks. So I have one line with 4 sets. So this is set 0, 1, 2, and 3. And then this is line 1, set 0, 1, 2, and 3. And this would be the fully associative case, in which I don't need any index bits because I only have one line. The fully associative case only has one line, so you know where it goes. It's just a matter of determining where it is, in which set it is. In this case, we have 8 sets here, because we have 8 blocks. We have 8 sets, and we know that it's going to go into one of them. We're going to talk about how we determine that. And then to find out, because the block, A block, could be in any of these 8, that's what we do the searches in parallel and determine which block the item is. So you can conceptually look at sets as being across the line. So the associativity tells you how many sets you have horizontally in a line of cache. The number of lines tells you how many you have vertically. And those need to be indexed. So examples that you can start thinking about is for a sequence, depending on how you draw these conceptual organizations. you can start looking at address sequences and seeing where it maps to, where the data maps to. So let's look at how a diagram, start constructing a diagram for set associative caches. So here we have 4 blocks, okay? And oops. So here we have 4 blocks, and actually this is a this is the typo. This is wrong. This is a direct map case. It actually only has 2 blocks, and it only requires 1 bit index. So this is a typo in the slides, okay? So with the tables, how I showed you the tables, you can start looking at block accesses given the associativity, and of course if it's direct mapped, the associativity is 0. There is no associativity at all. There is only 1 set per line of cache. And you can, using these tables, you can start looking at your where the items go and practice with that. Let's look at this one. Again, the tables will look like this. Is the direct map case, okay? This would be a 2-way set associative, okay? So now you can see the 2 sets. So this would be the data, this would be the tag. So this is how the tables get constructed to look at the allocation of items. All right, so this is a better diagram. So here we have how we would parse and structure the architecture for a 2-way set associative cache. So here we have 1 line of cache, and we have separated it because they each have their own valid bits and their own tags. They're going to require their own search and validate logic. So let's say that the first bit is going to be an offset, but then we're going to have an index. And let's say that if this was 1,000 here, okay, then you would need 10 bits for the address, and then the rest would be the tag. But the main idea here for set associative caches is that you have replication of the search and validation logic, and you have multiple sets across. We'll have a better diagram later on. And again, some more examples of the same table that we would use to keep track of the accesses. So you're going to get the slides for this today, and you'll be able to practice these examples and exercises. So you would populate them like that. So So several examples that you're going to get in the slides. I'm not going to read it to you, but again, you'll get the slides today. And the slides have different examples that you should go through. There is one example, and we show you what the final content is, so you can compare after you construct your table. There is a second example with the table. And there is a third example with the table. So different sets. So this is A-way set associative. And there is a fourth example. So as we wrap this up, let's talk about a couple of questions. How much associativity do we have? Well, again, as I have mentioned, anything that have to do with cache, you have to simulate, because it's not a an analytically closed system, so you have to simulate it. And for example, you would get numbers for the miss rate like this. So this is a system with 64 kilobytes of data cache, 16 words per block, and using the spec 2000 benchmark. So what you will find, an important sort of overarching conclusion, is that as you increase the associativity, your miss rate will go down, but with diminishing returns. So you can see here from 10 to 8, 8.6, 8.3, 8.1. So when you do your simulation and you plot your data for the miss rate versus associativity, you pick the best inflection point that gives you the highest return on the complexity that you're going to incur for having higher associativity. So in this case, I can sort of visualize this this data, and probably either two-way or four-way, which is not terribly complex, would be a good choice. Beyond 4, the complexity of associativity starts increasing, not only because of the duplication of the logic for the search and validation, but also for something that we're going to talk about next, which is now that you can now that you can place a block from the lower level in the cache, and now you have this flexibility depending on the associativity. How do you know which one you want to replace? Because you're going to replace one of them, and before you didn't have to ask this question, because with direct mapped you could only replace one. There was only a direct mapping to a block in the cache, but now you have associativity and you can go in any number of blocks in the cache. So how do you choose? Okay, so we're going to talk about that later, and this actually is in this slides is the best diagram that depicts a four-way set associative cache. So we can see clearly the lines of cache. It has 256 lines, and each line has 4 sets, and each set has its own tag, its own valid bit, and you can see how you would decompose the address. So this is a 32-bit address. It's byte addressable, so it has a byte offset, and then we require 8 bits to index 256 lines, and then the rest is the tag. For each line, we have 4 sets. So we have to do the searches and the validation in parallel, and then we can find out which one. Only one of these outputs of the AND gates is going to be a hit. And then we can order that saying that if we have a hit in any of them, we have a hit. It's because it's in one of them. And then from the individual searches, we can find out which one of the data or the block, which one is the data, and we can multiplex that out and pass it to the processor. This is an architectural diagram. It's not a schematic. It's not exactly, I mean, these lines here, obviously, that implies an encoder. There should be an encoder there. But again, just to abstract the functionality, what this is saying is that we use the information of the 4 hits to basically multiplex the block that is the one that we're looking for, because that's where the search was successful. So this is a very good diagram of a set associative cache, and if we were talking about for the same size of a storage, if we were going to draw a direct map, now this 4 sets will come down here. So instead of 256, I would have 1024, and that would be a direct map, same storage. And I would have more index bits and fewer tag bits. If I wanted to have two-way set associative, because remember this is 4-way, if I wanted to have two-way set associative, this would be twice as long, and this 2 would not be here. So this would go from 0 to 511, and I would need 9 bits for the index, and I would have 21 for the tag. So you can visualize the number of lines of cache for giving a storage amount, okay? For giving a storage, the number of sets or the associativity gives you how wide the cache structure is, and the number of lines gives you how tall it is. So in this case, however you organize it, given certain associativity, 4, 2, or none, or direct, this here you have, if we assume that the data or the block is a single word, 32 bits, so that's 4 bytes. So here you have 4 bytes, so each one of this is 1 kilobyte. So this is a 4 kilobyte cache, however you organize it, depending the associativity and the number of lines. All right, so let's go back to that question that I introduced before. How do you replace a block now that you have some options? That is called the replacement policy. That is called the replacement policy, and there are mainly 3 that are used. The first one is what is called least recently used, and what that means is that we're going to replace the block that has not been used for the longest time. So we have to keep track of that. And as I mentioned, beyond 4-way, it becomes quite complex to manage that. The other is the most recently used. So choose the one that has been on use for the shortest time. So that one, even though it's a valid policy, doesn't get used a lot. Okay. Another policy is random, which gives approximately the same performance as LRU if the associativity is high. So that is a nice, and we can generate random numbers with linear feedback shift registers in logic. So pseudo-random, that can give us some good performance with relatively low complexity for high associativity. Definitely the sort of a standard, the best performance is given by the LRU, but it's the most complex. Now, another one that I don't see here is round robin. Essentially, you go around the sets and just replace the next one in turn. And that also is very simple, but it doesn't, of course, it's not going to give you the same performance as LRU, because this takes into account that you are basically going to replace the block that has been there without being accessed, that's being there stale the longest, but you do have to keep track of that. So that is the replacement policy, which is one important design consideration only when you have associativity, when you have to choose which block to replace. Now let's talk about multi-level caches. So all the discussion that we've had so far is being predicated upon the assumption that we have a level 1 cache and then we have the memory, the main memory below that, and that's not really realistic. Modern systems, they have usually 3 levels of cache these days with multi-core processors. Definitely 3 levels is the norm. Now, all cache memory is made of SRAM, so it's going to be faster than DRAM. It's going to be smaller, but as you increase the size of the cache, it's going to become slower. And this is strictly a function of the physical construction, the RC delays on the actual lines of the circuitry, and the sheer size of the module. So level 2 is going to be faster than DRAM, so putting it there, but it's going to be slower than level 1 because it's going to be larger. And then you can have a level 3 that is larger than level 2 and yet faster than DRAM, and then you can have finally the DRAM. So that's the concept behind multi-level caches, and again, the norm these days is at least 2 levels. So let's look at why we would want that. So let's say we have a processor with a base CPI of 1 and a clock rate of 5 gigahertz. And let's assume that the main memory has an access time of 100 nanoseconds. And just to put it in perspective, 5 gigahertz is 0.2 nanoseconds. So let's say that the miss rate per instruction on the level 1 is 2%. And what we want to do is we want to know how much faster the processor would be effectively if we add a secondary cache that has a 5 nanosecond access time versus 100. But remember, the access time for level 1, keeping up with the CPU, is 0.2 nanoseconds. So here, level 2 is 25 times slower. 25 times slower than level 1. DRAM is 20 times slower than level 2. And if we didn't have this one, and we go from level 1 to DRAM, this is hundreds of times, 500 times lower than level 1. So what would be the advantage? Because now we don't get anything for free. Now we're having this other memory that is bigger than level 1, which is redundant, because in caches all the levels are redundant with respect to each other. So if we're going to make that investment, we want to see what we gain, how much faster the processor would be. Because remember, we have that redundancy. Everything that is in level 1 would be in level 2 and more. Everything that is in level 2 would be in DRAM and more. So if we made that investment, how much effectively faster the processor is going to be with this cycle time or this access time. And now, because it's going to be larger, the miss rate on level 2 is going to be 0.5%. So we have a miss rate on level 1 of 2% because it has certain size, but now level 2 is larger. So if we have a miss in level 2, and we only have a miss in level 2 if we already had a miss in level 1, because we went to get something from 2 to 1 and then it's not there, so it's in the lower level, which is the DRAM in this case. So miss on level 1, 2%, miss on level 2, 0.5% because it's larger than level 1. So what would be the advantage of that, of putting that level 2? Okay? So here we have base CPI of 1 with that clock rate, miss rate on level 1, 2%, main memory access time, 100 nanoseconds. Let's just do the calculation for not having the case where we don't have level 2. So we go from, if we have a miss on level 1, we have to go to DRAM. So the effective CPI would be 1 for the hits times the miss rate on level 1, which we said that it was 2%, times the number of cycles. The number of cycles that we will have to wait to access that block in main memory. And we said that the frequency of the processor is 5 gigahertz, so that's 0.2 nanoseconds, and the access time of the DRAM is 100 nanoseconds, so that would be 500 cycles. So the penalty is 500 cycles. So the effective CPI, or the effective performance, is 11. That means that a 5 gigahertz processor is really performing more like a less than 500 megahertz processor. So the performance degradation is more than 10 times. Really bad. Now let's add the level 2 cache with the 5 nanosecond access time and the miss rate to main memory as 0.5%. So the penalty now is the access time times the clock period for an L2. Well, I'll skip this one. If we have a primary miss with a level 2 miss as well, we still have to go to main memory, so we're going to have that 500 cycles of miss penalty because it's neither in level 1 and it's not in level 2 either. But what happens if we have a miss on level 1, but we have a hit on level 2. Then the penalty, instead of being 500 cycles, becomes 25, because now the next level after level 1, the access time there is not 100 nanoseconds anymore, is 5. So the equation for the effective performance becomes the base CPI plus the penalty for misses on the primary cache, the level 1, plus the penalty for misses on the secondary cache. And remember, the penalty here now is based on a 5 nanosecond access time. On the secondary, is still based on a 100 nanosecond access time. What is going to be changing is the miss rates. That because level 2 is much larger than level 1, we're going to have this much smaller miss rate of 0.5%. So here it is. Here's the new effective performance. You have the base CPI, the penalty for a miss on level 1, but a hit on level 2. That would be the 2% miss rate on level 1 times the new penalty. It's not 500 anymore, it's 25. But if you do have, or when you do have a miss on both level 1 and level 2, you have to add this penalty. But now the miss rate is 0.5%. And the penalty is still 500 cycles because you have to go to DRAM. So now the new performance, the effective CPI, is 4 instead of 11. So our performance degradation, instead of being more than 10, is 4. And if we compare the performance of the system with level 2 cache versus the system without it, we'll see that that system is almost 3 times faster. So that's how multi-level caches help you keep the performance high. And if you did the same analysis with level 3, what you will find is that you can defer now this 500, which is the DRAM access, later to a level 3 miss, and it's going to be much larger than level 2. So the miss rate is going to be much smaller than 0.5%. So it's going to affect the base CPI even less. And then this penalty for level 2, since it's going to level 3, is going to be lower than 500. So that also is beneficial. Again, you do have to keep putting all these redundant memories and bigger. So at some point, it becomes a cost performance improvement trade-off. And that's part of the analysis and decisions of what overall cache strategy and architecture you will have in a processor system. So what are the considerations as we wrap up here? Hopefully, it is obvious to you now that for the level 1, what we want to focus is on access time, reduce the access time, so that we can keep up with the processor. That's one big requirement. So a small access time, so we're going to make it as small as possible so we can have a reasonable miss rate, but we don't degrade the speed or the access time for the sake of making it larger. For level 2, what we want to do is minimize the miss rate. So we're going to now make it bigger and have a reasonable access time, but we want to essentially avoid the probability that we have to go to DRAM. So and that's why the level 1 is much smaller. In a multi-level cache, the level 1 can be, and it is much smaller than if you only had a single level. And the block size is also smaller than the level 2 block size. Again, because you're trying to have that, you're trying to have that access time keep up with the CPU. Some of the other issues that perhaps we'll discuss in subsequent presentations is how the cache idea and the multi-cache organizations interact with the concept of advanced CPUs. So we discussed in chapter 4 out of order execution, the pending stores and loads, that type of interaction and concepts of advanced CPUs. We looked at the reservation station concept for CPUs that have parallel pipelines. So how does that interact with the whole cache? And the short answer is that level 1 is very much, even though it's not part of the CPU, the design of level 1 is very much intertwined with the CPU. And ultimately, of course, these issues of performance and with this level of complexity depends on the program data flow. You can run simulations with real programs, with benchmarks, but it's all about simulation because you really cannot come up with an equation to really embody these arrangements. We're going to stop here.